In this video, I will discuss a JEE Advanced PYQ based on the topics EMI and RC circuit. First, some basics. The aim of induced in a closed path is given as d phi by dt, where phi is the flux linking this closed path. This is Faraday's law of electromagnetic induction, and the flux linking this closed path is given as integral b dot dA over this entire area. In RC circuit, a resistor and a capacitor in series with a same constant voltage source, but there is a switch here. So initially the switch is open and the switch is closed at time t equal to 0. So as soon as the switch is closed at time t equal to 0 plus, the capacitor will act as a short circuit. So it's as if it's not just connected by a wire. So in this case, the current flowing in this circuit will be the total EMF divided with resistance, value say R. So this is the current at 0 plus. After that, the charge will start building up here, positive charge and minus charge here, and the amount of voltage available across the resistance will drop down. So the currents will start decaying. So at time t equal to, say after a large amount of time, the current at t equal to infinity will be 0. The capacitor will act as a open circuit. All this current movement will go in building up the charge, and the charge that is being built on this capacitor, that's equal to C into V. This entire E will appear across there. So this is the charge on this capacitor at t equal to infinity or after a long time. The basic thing that's used in this question is Ampere's circuit law, which gives current and the magnetic field relation. So B here, current is given as integral B dot dl over a closed path equal to mu naught into I. I is the current which is enclosed in this path. For example, this is a closed path, say C. So if you do B dot dl along this closed path and some current is flowing, so sum of B dot dl along this closed contour equal to mu naught into I, which is passing through this contour. So this is Ampere's circuit law. So based on this ideas, we can solve this JEE Advanced question. This is a question. A long straight wire carries a current I equal to 2 amps. A semicircular conducting rod is placed beside it in two conducting parallel rails of negligible resistance. Both rails are parallel to the wire. The wire, the rod, and the rails lie in the same horizontal plane as shown in the figure. Two ends of semicircular rod are at distances 1 cm and 4 cm from the wire. At time t equal to 0, the rod starts moving on the rails with a speed v equal to 3 meter per second. See the figure. The resistor R 1.4 ohms and a capacitor C0 5 microfarad are connected in series between the rails. At time t equal to 0, C0 is uncharged which of the following statement are correct? Mu naught equal to 4 pi 10 to the minus 7 SI units. Take ln 2 equal to 0.7. Statements are: statement A, maximum current through R is 1.2 into 10 to the minus 6 ampere. Statement B, maximum current through R 3.8 10 to the minus 6. Statement C, maximum charge on capacitor C0 is 8.4 10 to the minus 12 coulomb. Statement D, maximum charge on capacitor C0 is 2.4 10 to the minus 12 coulomb. So you have to check which of the statements are true. Basically, find the maximum current and the maximum charge on the RC circuit. You can pause and run this question. So, because of this current, there will be magnetic field in this direction, cross. It's given by right hand rule, thumb along the direction of the current. So the 4 fingers will curl. Okay, and this magnetic field will produce a flux linking this circuit. This is a closed circuit. Okay, so that flux will change as a function of time because this thing is moving. So more area is coming under this closed path. So the flux will increase as a function of time. So this flux phi, which is linking this closed path, we can consider is made up of two parts. Phi 1, which is the semicircular region, plus phi of the rectangular region. This is the rectangular region. And the top one is semicircular region. So the flux of this entire closed path is this part, semicircular part, plus the flux of the rectangular part. As this semicircular rod is moving up, this part of the area is not changing. Even the magnetic field on this part will not change because magnetic field is only a function of, let me take this as x direction. Magnetic field is function of x because as you go far away, if we are going far away from the source, so the magnetic field will get weaker, but the magnetic field here is same even if the rod goes up. So the flux linking this semicircular part is constant. So this is a constant flux. This rectangular region flux is a variable because the area is increasing with time. So this phi will increase with time. So flux of this rectangular part we can calculate. First, you have to find the magnetic field due to this current carrying wire at any point. So let me take this strip here of thickness dx at a distance x from the wire. This is the origin for x, and x is measured from this x equal to 0. So area of the strip is dx into, and let me call this as y equal to 0, and this much is y. This semicircular part starting, this much is y. So area of the strip is y into dx, and magnetic field at x I can find out by Ampere's circular law, which is integral b dot dl equal to mu naught into I over the closed contour C. So here I will take or you can still use the formula if you know the formula for to do the contour to do this Ampere's circular law. So B and DL are in the same direction, so it become B into DL is 2 pi, the circumference of the circle which is x, that's equal to the current enclosed is mu naught into I. So magnetic is function of x, it's mu naught by 2 pi into I by x. If you remember this formula, I can straight away use this formula rather than deriving it. So this flux here, the rectangular plot, is integral b as a function of x dot dA, and this area vector and this b are in the same direction. So b dot dA is b into dA into cos 0, and this b as a function of x is this one. And this area of the strip is dx into y, and as the thing moves, y will increase. So induced EMF E is d phi by dt, and the first term is constant. So d by dt of the first term is 0, so only the second term will come. It's mu naught. Before that, I have to integrate this one. This is just b. This integration I have to do before coming to the EMF calculation. B dot dA. So this is from x equal to, see, this one is x1, and from here to here, the second rail, it's x2. So this will give me y for a given y. This integration is for a particular instant. Other instant y is fixed. So this integration over x. So mu naught by 2 pi I. So this is ln x. So it will be ln, and you put the limit will be x2 by x1 into y. And x2 and x1 are given as 4 and 1. So this is ln 4 into y. So now to get the EMF, I got the flux. Use Faraday's law of electromagnetic induction. Induced EMF is d phi by dt. The first term is 0, only the second flux will come. So it's d by dt of this term. And 4 I can write as 2 square. So 1, 2 will go, or I can just keep this one. Mu naught by 4 pi I. Ln 4 is 2 square, so it's 2 ln 2. And then dy by dt. dy by dt is how fast this part is moving up, that's same as this velocity into v. Just differentiate this one. Mu naught by 4 pi. I is a constant. And this ln 4 I get as 2 ln 2 because 4 is 2 square. So 2 will come up. And then dy by dt is the velocity of the rod v. So all these values are given. So you can find this value of the EMF. Mu naught by 4 pi is 10 to the minus 7 in SI units. Current is 2 amps into 2 ln 2 is given as 0.7 into the velocity of the rod, semicircular rod, is 3 meters per second. So this will give me 12 into 10 raised to minus 7 into 0.7 SI units volts. And another interesting thing to notice, this voltage is a constant voltage, it's not a function of time. So it's like a DC source. That makes the problem simple. So now it's a simple RC circuit. So the maximum current is the current at time t equal to 0, because at time t equal to 0, the capacitor acts as a short circuit. So maximum current is the current at time t equal to 0. and that will be due to the current acting in this voltage source across this resistance. So this E by R, RC circuit, and this is the voltage source because of this flux linkage. So at time t equal to 0, capacitor is short, so the full voltage will come across this R. So the current will be E by R, and E is this much, and value of R is 1.4 ohms. So 12 into 10 raised to minus 7 into 0.7 divided by 1.4. So this will go 2 times. So it is 6 into 10 raised to minus 7 amps. It's a mistake. Here there is a mistake. It's mu naught by 2 pi. Where it suddenly become 4. So mu naught by 2 pi. So the 2 pi should come here. So this will be 2 into 10 raised to minus 7. So 2 will become 24. So into 2. Into 2. So it's 12 into 10 raised to minus 7 is the maximum current. That is same as 1.2 into 10 raised to minus 6. So option E is correct. So B is wrong. And then you have to find the maximum charge. So the capacitor gets fully charged at infinite time. And that charging will happen because of the entire voltage appearing across the capacitor. So to find that value, you just have to do Q equal to C into V, where V is the entire EMF. So the maximum is C into the entire EMF, that's 24 into 10 raised to minus 7 into 0.7, and the capacitance value is 5 micro. Micro is 10 raised to minus 6. So this into 24 into 10 raised to minus 7 into 0.7. So 5 and 24 I can combine as this. 24 is 2 into 12, 1 2 I can push it here, so it will become 120 into 0.7 into 10 raised to minus 13. This is 10 raised to minus 6, 10 raised to minus 1, minus 13. So 1 0 I can knock it here, so it will become 10 raised to minus 12. And then 12 6s, 12 7s are 84. So 8.4. 1 0 will become 10 raised to minus 12. So 12 6 are 7, 12 7s are 84. So it will become 8.4. So this many coulombs. So option C, 8.4 10 raised to minus 12 coulombs is the correct answer. So D is obviously wrong. So C is true, D is wrong. Correct statements are A and C. A and C are the correct statements. This one I explained here. The flux in this closed path where the current is flowing is flux through the semicircular region plus the rectangular region. Due to the closed circuit, so the flux linking this thing can be divided into 2 parts. One is the semicircular part, this much, and the rectangular part. As this thing moves, the semicircular part area is fixed, it will not change. But this rectangular part area will grow. So the flux is flux of the semicircular part, which is the constant, plus flux in the rectangular part, which is integral B dot dA, and B is a function of x. So this second part of the flux is Ampere's circuit law, mu naught by I divided by 2 pi x. and this area D is dx into y. So mu naught by 2 pi into y ln of x2 by x1. So this variable is x. So integrate dx by x, which is ln x. And you have to put the limits x1 to x2. And this x2 by x1 is 4 by 1, which is 4. This one. From this, you get d5 by dt as 4 into 10, no, this value. And mu naught by pi is 4 into 10 minus 7. So you from this much. So the current maximum is the maximum current at t equal to 0, because at t equal to 0, RC circuit, the current will be maximum and the capacitor acting as a short circuit. So current is basically the voltage or the EMF divided by the resistance value. Resistance value is 1.4. So from this, resistance value is 1.4. So from this you get the current maximum as 12 into 10 minus 7, which is 1.2 into 10 minus 7 is option E. And the capacitor has the maximum charge at infinite time. So that's C into V, and this V is the entire EMF which will act across the capacitor, because the current will die down to 0. So the capacitor value is 5 microfarad and voltage is 24 into 0.7 into 10 minus 7. So this will become 8.4 into 10 minus 12. So option C is true.